November 16, 1896, Niagara Falls, New York. The massive transformers hummed to life in George Westinghouse's power station, channeling 26 miles of electrical current toward Buffalo's streetlights. European electrical engineers had declared this distance impossible for reliable power transmission. Through the industrial roar of America's first long-distance electrical grid, Westinghouse's AC transformers performed with precision that would outlast anything built in the next century. No planned obsolescence, no disposable components, no expectation of 15-year replacement cycles. These machines were engineered to run for generations using materials and manufacturing standards that modern utilities abandoned decades ago. In European power systems, transformers required constant maintenance and frequent replacement. Most electrical equipment carried warranties measured in years, not decades. The Americans were building with engineering philosophy the modern world has forgotten. Solid copper windings, paper insulation soaked in mineral oil, cast iron housings built like battleship armor, manufacturing precision that treated every transformer as a 50-year investment, not a consumable product. 130 years later, many of Westinghouse's original transformers still power American cities. While modern units fail within 15 years, these industrial monuments prove that planned obsolescence wasn't always the American way. The question isn't why old transformers last forever. The question is why we stopped building them to. The summer heat of 1885 pressed down on New York's Pearl Street as Thomas Edison surveyed his electric empire from the window of his cramped generating station. Steam hissed from the coal-fired boilers that powered his direct current dynamos, filling the basement facility with oppressive humidity that matched Edison's growing frustration. His Pearl Street station, the crown jewel of American electrical innovation, could illuminate exactly 47 city blocks before voltage dropped to unusable levels. Beyond that narrow radius, Edison's 110-volt system became worthless, defeated by the fundamental physics of electrical resistance that no amount of genius could overcome. Edison pressed his palm against the window glass, watching horse-drawn carriages navigate between the thick copper cables that snaked beneath the cobblestones. Those cables, each as thick as a man's wrist and worth more than most workers earned in a year, represented the crushing economics of direct current transmission. To push electricity just 9/10 of a mile required copper conductors so massive that installation costs alone exceeded the annual budgets of entire townships. Every additional block demanded exponentially thicker wires, creating a geometric progression toward impossibility that trapped Edison's system within walking distance of its generating plants. The irony wasn't lost on America's most celebrated inventor. His incandescent bulbs had conquered the darkness inside buildings, but entire regions remained beyond his reach. Rural America, where 80% of the population still lived by candlelight, represented an untapped market worth millions of dollars that Edison's technology simply couldn't access. The copper costs alone would bankrupt any company foolish enough to attempt long-distance DC transmission, and Edison's engineers had calculated the mathematics repeatedly, hoping for different results that never materialized. Francis Upton, Edison's chief mathematician, spread voltage drop calculations across the wooden table that dominated the Pearl Street office. The numbers told the same story they'd been telling for 5 years. Direct current lost 30% of its power within half a mile, 50% within 3/4 of a mile, and became commercially worthless beyond the 1-mile threshold. "We could build generating stations every few blocks," Upton suggested, adjusting his wire-rimmed spectacles as he reviewed the financial projections. Smaller plants, closer distribution. Edison shook his head, recognizing the economic trap that suggestion represented. Every generating station required coal deliveries, skilled operators, maintenance crews, and expensive steam equipment. Multiplying those costs across hundreds of neighborhood plants would price electricity beyond the reach of ordinary Americans, limiting his market to wealthy urban districts that could afford premium power. The vision of electric light illuminating every American home would remain forever out of reach, strangled by the economic realities of short-range transmission. Meanwhile, 250 miles west in Pittsburgh, George Westinghouse sat in his mahogany-paneled library, absorbed in a technical journal from London that would change everything. The article, published in Engineering magazine, described European alternating current systems that employed transformers to step up voltage for long-distance transmission, then step down that same power for safe household use. The concept seemed almost magical: electricity that could travel 7 miles at high voltage, then transform itself to harmless household current at the moment of consumption. Westinghouse read the technical specifications twice, then a third time, before the full implications crystallized. While Edison's system required generating stations within blocks of customers, alternating current could transmit power from centralized plants across entire counties. Rural communities, industrial districts, and suburban developments previously beyond electrical reach would suddenly become viable markets. The economic advantages were staggering. Instead of hundreds of small generating plants, a single large facility could power entire regions with unprecedented efficiency. The 39-year-old industrialist had built his fortune on railroad air brakes, a safety innovation that prevented countless accidents by allowing engineers to stop entire trains with compressed air systems. That success had taught him to recognize transformative technologies before competitors understood their potential, and the European AC descriptions triggered the same intuitive recognition that had made him wealthy. This wasn't merely an improvement over Edison's system, it represented a complete paradigm shift that would restructure America's entire electrical industry. Westinghouse's mechanical background gave him advantages that pure electrical theorists lacked. He understood power transmission from his railroad experience, where locomotives needed to deliver maximum force across varying distances and conditions. The transformer principle reminded him of gear ratios in mechanical systems. High voltage for efficient transmission corresponded to high gear ratios for speed, while low voltage for household safety matched low gears for control and precision. The analogy wasn't perfect, but it provided intuitive understanding that purely electrical engineers sometimes missed. By September of 1885, Westinghouse had committed $2 million of his personal fortune to acquiring European AC patents and hiring the engineering talent necessary to adapt those systems for American conditions. His Pittsburgh workshops began producing transformers based on European designs, but modified for American voltage standards and manufacturing capabilities. The gamble represented everything he'd earned from railroad innovations, risked on electrical theories that most American engineers dismissed as impractical foreign experiments. The established wisdom supported Edison's position completely. Direct current was stable, predictable, and backed by over 1,000 patents that Edison had accumulated through relentless experimentation. His Pearl Street station had operated reliably for 3 years, proving that American electrical systems could match European achievements using proven American engineering methods. Why abandon successful technology for untested alternating current systems that operated at dangerous high voltages during transmission? Yet the mathematics of long-distance power distribution couldn't be argued away by appeals to established wisdom or inventor reputation. Edison's system would forever remain confined to dense urban districts, while Westinghouse's alternating current promised to electrify the American continent itself. William Stanley, Jr. arrived at Westinghouse's Pittsburgh headquarters in January of 1886, carrying a leather satchel filled with transformer calculations that would prove alternating current's commercial viability on American soil. The 29-year-old Massachusetts engineer had spent the previous 6 months redesigning European transformer specifications for American manufacturing capabilities, replacing metric measurements with standard American dimensions and recalculating voltage ratios for the 110-volt household standard that Edison had established. Stanley's meticulous attention to insulation materials and core lamination techniques addressed the practical manufacturing challenges that separated theoretical European patents from reliable American electrical equipment. Westinghouse recognized in Stanley the same methodical precision that had made his railroad air brake systems virtually failure-proof. While other engineers dismissed transformers as complex European curiosities, Stanley understood that successful voltage conversion required obsessive attention to materials science and electromagnetic field calculations. His transformer prototypes used specially treated paper insulation soaked in mineral oil, surrounded by laminated iron cores that minimized energy losses during voltage conversion. These weren't mere copies of European designs, but systematic improvements that addressed American manufacturing standards and operational requirements. The partnership between Westinghouse's business vision and Stanley's engineering craftsmanship produced America's first commercial AC power system in Great Barrington, Massachusetts, where Stanley had convinced local investors to fund a demonstration project. The installation generated 500 volts at the central power station, then used Stanley's transformers to reduce that voltage to 100 volts for household lighting and commercial applications. The system's ability to safely manage high transmission voltages while delivering low household voltages proved that alternating current could combine Edison's safety standards with transmission distances that DC technology could never achieve. Great Barrington's main street illuminated on March 20th, 1886, with electric lights powered from a generating station over half a mile away. Local residents gathered along the wooden sidewalks to witness the impossible, bright incandescent bulbs receiving power, transmitted at distances that would have rendered Edison's DC system completely useless. The demonstration attracted electrical engineers from across New England, many of whom had traveled expecting to witness spectacular failures or dangerous accidents. Instead, they observed stable voltage conversion that maintained consistent lighting across the entire distribution network, with transformer efficiency ratings exceeding 90%. Stanley's success in Great Barrington validated Westinghouse's massive financial gamble on alternating current technology, but it also attracted the attention of an unemployed Serbian immigrant whose polyphase motor patents would transform AC from a lighting curiosity into a complete electrical system capable of powering American industry. Nicola Tesla had arrived in New York 2 years earlier with little more than the clothes he wore and a letter of introduction to Thomas Edison, hoping to find employment with America's most famous electrical inventor. Tesla's relationship with Edison had soured over a disputed $50,000 bonus that Edison had promised for improving DC generator efficiency, then refused to pay when Tesla delivered the requested improvements. The brilliant immigrant's rotating magnetic field theories had impressed Edison's engineers, but Edison himself dismissed alternating current as a dangerous European fad that would never compete with proven direct current technology. Tesla's departure from Edison's employment in 1885 left him temporarily destitute, digging ditches for $2 per day while developing polyphase motor concepts that would revolutionize electrical power transmission. Westinghouse's representatives contacted Tesla in May of 1886, offering not just employment, but a partnership that would combine Tesla's motor patents with Stanley's transformer systems to create the world's first complete AC electrical infrastructure. Tesla's polyphase design solved the fundamental limitation that had confined alternating current to lighting applications. Previous AC systems couldn't efficiently power motors, limiting their industrial applications to illumination and heating. Tesla's rotating magnetic field principle enabled AC motors that operated more efficiently than DC equivalents while maintaining the transmission advantages that transformers provided. The financial terms of Tesla's partnership with Westinghouse reflected the transformative potential of polyphase technology. Westinghouse agreed to pay $60,000 for Tesla's existing patents, plus royalty payments of $2.50 for every horsepower of AC motor capacity sold by Westinghouse companies. Conservative projections suggested those royalties could exceed $1 million annually once AC systems achieved widespread adoption, making Tesla potentially wealthy beyond his modest immigrant beginnings. Tesla's polyphase motor demonstrations at Westinghouse's Pittsburgh laboratories convinced skeptical investors that alternating current represented a complete electrical solution, not merely an improved lighting system. His motors operated using three-phase AC power that provided smoother torque delivery than single-phase systems, while maintaining the voltage conversion flexibility that transformers enabled. Industrial applications that had remained loyal to Edison's DC systems due to motor requirements suddenly became viable markets for Westinghouse's AC technology. By December of 1886, Westinghouse had installed 30 AC power systems across the northeastern United States, each demonstrating transmission distances that Edison's technology couldn't match. The systems varied in size from small-town installations serving a few hundred customers to industrial complexes requiring thousands of horsepower for manufacturing equipment. Tesla's polyphase motors powered textile mills in Massachusetts, steel rolling mills in Pennsylvania, and grain elevators in Ohio, proving that alternating current could handle the heaviest industrial demands while maintaining the transmission efficiency that transformers provided. The rapid expansion of Westinghouse AC installations created a troubling pattern that Edison's business associates couldn't ignore. Within 12 months of Tesla's partnership with Westinghouse, AC systems had captured nearly 30% of new electrical installations across the northeastern United States. Edison's DC empire, which had required 7 years to establish 121 generating stations, suddenly faced competition from a technology that achieved comparable market penetration in less than 2 years. Edison's response to this competitive threat would transform a technical disagreement between electrical engineers into a propaganda war that used public fear, legislative manipulation, and spectacular demonstrations of AC's lethal potential to preserve DC's commercial dominance through political rather than engineering superiority. Edison's counterattack began in December of 1887 with a carefully orchestrated publicity campaign that transformed technical engineering disputes into visceral public fear. Harold P. Brown, a relatively unknown electrical engineer who had witnessed several gruesome AC electrocution accidents in New York's hastily installed power lines, became Edison's most effective weapon in the propaganda war against alternating current. Brown's genuine horror at seeing workmen killed by high-voltage AC wires provided the emotional authenticity that Edison's campaign required, even as Edison's company secretly funded Brown's increasingly theatrical demonstrations of AC's lethal potential. Brown's first public demonstration took place at Columbia College on July 30th, 1888, before an audience of electrical engineers, journalists, and city officials who had gathered expecting a technical presentation on electrical safety standards. Instead, they witnessed Brown electrocute a series of stray dogs using progressively higher voltages, first with Edison's direct current, then with Westinghouse's alternating current. The dogs survived multiple DC shocks at voltages up to 1,000 volts, but died almost instantly when subjected to AC current at significantly lower voltages. Brown's conclusion seemed inescapable. Alternating current was inherently more dangerous than direct current, regardless of voltage levels. The demonstration's scientific validity was questionable at best. Brown had weakened the animals with repeated DC shocks before applying AC current, and his equipment measurements were imprecise by any rigorous standards. More importantly, he ignored the fundamental safety principle that proper insulation and circuit protection could make any electrical system safe for household use. But the visceral impact of watching animals die from AC electrocution generated newspaper headlines that no amount of technical explanation could overcome. New York's evening papers carried dramatic accounts of the deadly alternating current and Westinghouse's killer electricity that terrified readers who lacked the technical background to evaluate Brown's claims critically. Edison amplified Brown's message through his extensive network of business relationships and political connections, financing additional demonstrations in cities where Westinghouse was competing for municipal lighting contracts. The campaign's psychological sophistication reflected Edison's understanding that public policy decisions were driven more by emotional reactions than technical analysis. Most city council members and utility commissioners lacked the engineering background necessary to evaluate competing electrical systems objectively, making them vulnerable to fear-based arguments that sidestepped complex technical discussions about voltage regulation, transformer efficiency, and power transmission economics. The propaganda war's most macabre chapter began when New York State Legislature commissioned the development of a more humane method of execution to replace hanging, which often resulted in prolonged suffering when performed incorrectly. Brown volunteered to design an electric chair using alternating current, arguing that AC's superior killing power would guarantee quick, painless death for condemned prisoners. Edison's financial backing enabled Brown to construct the device using Westinghouse generators and transformers, creating a direct association between Westinghouse's technology and state-sanctioned execution in the public mind. William Kemmler, convicted of murdering his wife with a hatchet, became the first person executed by alternating current on August 6, 1890, in Auburn State Prison. The execution was intended to demonstrate AC's lethal efficiency while simultaneously promoting the idea that alternating current was too dangerous for household use. Instead, the botched execution became a propaganda disaster that highlighted the electric chair's design flaws, rather than AC's inherent dangers. The first 17-second shock failed to kill Kemmler, leaving him unconscious, but still breathing. Prison officials applied a second shock that lasted over a minute, filling the execution chamber with the smell of burning flesh as Kemmler's body caught fire. Newspaper reporters described the execution as an awful spectacle, far worse than hanging, and questioned whether electrical execution represented progress in criminal justice or a return to medieval torture methods. The gruesome details undermined Brown's claims about AC's clean killing power while generating sympathy for Westinghouse, who had unsuccessfully attempted to prevent his equipment from being used for executions. Rather than associating AC with quick, efficient death, the Kemmler execution also suggested that even Brown's carefully designed electrical apparatus couldn't reliably kill human beings without causing prolonged suffering. Westinghouse responded to Edison's propaganda campaign with a strategy that emphasized engineering facts over emotional manipulation. Rather than engaging in public debates about animal electrocution or capital punishment, Westinghouse focused on demonstrating AC's practical advantages through successful installations that served real communities with reliable, safe electrical power. His engineers published detailed safety statistics showing that properly installed AC systems had accident rates comparable to DC installations, while providing transmission distances that DC technology simply couldn't match. The most effective element of Westinghouse's response was economic rather than emotional. To compete directly with Edison's established market presence, Westinghouse began selling AC systems at significant losses, sometimes bidding 50% below cost on municipal lighting contracts to demonstrate his technology's reliability in high-profile installations. This strategy required enormous financial resources that only Westinghouse's railroad profits could sustain, but it placed working AC systems in communities across America where residents could evaluate the technology's safety and effectiveness through personal experience rather than newspaper sensationalism. Westinghouse's willingness to sacrifice short-term profits for long-term market position reflected his confidence that superior engineering would eventually overcome fear-based marketing campaigns. Unlike Edison, who had built his reputation through individual invention and patent accumulation, Westinghouse understood that complex technological systems succeeded through systematic engineering excellence rather than promotional genius. AC's technical advantages were so overwhelming that sustained exposure to working systems would inevitably convince rational observers of its superiority over DC alternatives. The propaganda war's intensity reflected both inventors' recognition that America's electrical future hung in the balance. Edison's DC empire represented millions of dollars in existing investments, hundreds of patents, and the industrial infrastructure that had established him as America's most celebrated inventor. Westinghouse's AC system threatened to render those investments obsolete while transforming electrical power from an expensive urban luxury into a continental utility network that could serve every American community. The stakes were too high for purely technical competition. The winner would control the industry that would power 20th century America. By 1889, the propaganda war had reached a stalemate that favored neither technology decisively, setting the stage for direct competition in the most visible electrical contract of the 19th century. The Niagara Falls Power Company announced its ambitious hydroelectric project in February of 1891, proposing to harness the immense energy of Niagara Falls for electrical generation that would power Buffalo, New York, 26 miles away. The project's scale dwarfed any previous electrical installation. 100,000 horsepower of generating capacity that would require transmission distances beyond anything Edison's direct current technology could achieve. International engineering consultants estimated the project would require copper conductors weighing over 4,000 tons if DC transmission were attempted, creating cable costs alone that exceeded the project's entire budget allocation. Edison's proposal for the Niagara contract reflected his desperate attempt to preserve DC technology's commercial viability through brute force engineering solutions that ignored economic reality. His system required underground copper cables 6 inches in diameter, supported by massive concrete conduits that would transform the 26-mile transmission corridor into an industrial monument more expensive than the generating station itself. Even with these enormous conductors, Edison's calculations showed voltage losses exceeding 40% during transmission, requiring the generators to produce nearly twice the power that Buffalo would actually receive. The physical impossibility of Edison's DC proposal became apparent during site surveys that revealed the engineering challenges of installing massive copper cables across the Niagara River Gorge and through 26 miles of varied terrain, including rocky escarpments, swampland, and multiple river crossings. Each cable section would require custom-built support structures capable of withstanding the weight of solid copper conductors, while underground installation would demand excavation costs comparable to building a railroad between Niagara and Buffalo. The project's total construction budget couldn't accommodate even the copper requirements, much less the specialized installation infrastructure that DC transmission demanded. Westinghouse's AC proposal eliminated these obstacles through Tesla's polyphase system and Stanley's transformer technology, transmitting power at 11,000 volts through relatively lightweight cables that required conventional power line installation methods. The high transmission voltage reduced current flow by a factor of 100 compared to household voltage levels, dramatically minimizing both power losses and conductor requirements. At Buffalo's receiving stations, transformers would reduce the 11,000-volt transmission power to standard household voltages, providing the same electrical service that Edison's system offered, but delivered through economically viable transmission infrastructure. The engineering elegance of Westinghouse's solution impressed the International Commission of Experts, who evaluated competing proposals for technical feasibility and economic practicality. Lord Kelvin, Britain's most renowned physicist, initially favored DC transmission based on its proven reliability, but changed his recommendation after reviewing Tesla's polyphase calculations and Stanley's transformer efficiency data. The Commission's final report concluded that alternating current represented the only practical method for long-distance power transmission, and recommended AC technology despite Edison's fierce lobbying efforts. Even as the Niagara decision favored AC technology, a more immediate and visible contest emerged that would demonstrate the competing system's capabilities before millions of potential customers. Chicago's World's Columbian Exposition, celebrating the 400th anniversary of Columbus's arrival in America, required the largest electrical installation in human history to illuminate the fair's 600 acres of exhibition halls, midways, and architectural monuments. The contract specifications called for powering 93,000 incandescent bulbs plus arc lighting for outdoor areas, creating electrical demands that exceeded many entire cities' power consumption. General Electric, the company formed by Edison's merger with Thomson Houston, submitted a bid of $554,000 to illuminate the exposition using Edison's DC technology. The proposal required multiple generating stations distributed throughout the fairgrounds to overcome DC's transmission limitations with elaborate underground cable networks that would deliver power to individual exhibition buildings through the shortest possible routes. Despite the system's complexity and high installation costs, General Electric's bid reflected the established electrical industry's confidence that proven DC technology deserved premium pricing for such a prestigious installation. Westinghouse shocked the electrical industry by submitting a bid of $399,000, undercutting General Electric by over $150,000, while proposing to power the entire exposition from centralized AC generating stations. His bid was so aggressively low that competitors suspected mathematical errors or deliberate deception designed to win the contract through unsustainable pricing. Industry analysts calculated that Westinghouse would lose money on every aspect of the installation, from generator manufacturing to cable installation, making his bid appear financially suicidal. The exposition's organizing committee awarded the contract to Westinghouse in April of 1893. Despite concerns about his company's ability to deliver such an enormous electrical system at the proposed price. Westinghouse's willingness to accept substantial losses reflected his understanding that the World's Fair represented the ultimate proving ground for electrical technology, where success would establish AC's credibility before an international audience of potential customers, investors, and technical experts. Failure, conversely, would vindicate Edison's warnings about AC's impracticality and restore DC's dominance over American electrical markets. Tesla's polyphase generators and motors powered the exposition's electrical system through transformers that distributed power across the fairgrounds with unprecedented efficiency and reliability. The installation included innovations that became standard practice in subsequent electrical projects: centralized power generation, high-voltage transmission, and voltage conversion for different applications ranging from delicate exhibition lighting to powerful industrial machinery that operated rides and mechanical displays. Visitors witnessed electric motors running smoothly on AC power, contradicting Edison's claims that alternating current couldn't reliably operate industrial equipment. The exposition opened on May 1, 1893, with an electrical spectacular that illuminated Chicago's lakefront with the brilliance of artificial daylight. President Grover Cleveland activated the electrical system by pressing a telegraph key that started Tesla's polyphase generators, instantly powering thousands of lights that transformed the fairgrounds into what newspapers called a city of electric fire. Over the exposition's 6-month duration, 27 million visitors experienced electric lighting powered by AC technology, creating the largest public demonstration of electrical power in human history. The fair's electrical success established alternating current as a mature, reliable technology capable of handling the most demanding applications while providing economic advantages that DC systems couldn't match. More importantly, it demonstrated AC's potential for powering the industrial infrastructure that would define 20th century America, setting the stage for the final confrontation between competing electrical philosophies at Niagara Falls itself. The Niagara Falls Power Company's board of directors convened on October 15, 1893, to make the final decision between competing electrical systems that would determine America's power transmission future. Despite Edison's continued lobbying efforts and General Electric's promises of proven DC reliability, the mathematics of long-distance transmission had become impossible to ignore. Tesla's polyphase calculations demonstrated that AC could deliver 100,000 horsepower to Buffalo with less than 10% power loss, while Edison's DC proposal would lose nearly half its generated power during the 26-mile transmission journey, making the project economically unfeasible regardless of copper conductor size. Westinghouse's victory at Niagara represented more than a single contract award. It marked the moment when superior engineering definitively triumphed over marketing manipulation and established reputation. The power company's engineers had evaluated both systems using rigorous technical criteria rather than public relations campaigns, and AC's overwhelming advantages in transmission efficiency, installation costs, and operational flexibility made the decision inevitable. Edison's attempts to preserve DC dominance through propaganda and political influence had delayed but couldn't prevent the adoption of technically superior technology. Construction of the Niagara power plant began in January of 1894, with Tesla's polyphase generators as the centerpiece of an installation that would dwarf every previous electrical project in scale and ambition. The generators themselves represented marvels of precision engineering: 12-ton rotating assemblies that produced 3-phase alternating current at 2,300 volts, designed to operate continuously for decades with minimal maintenance requirements. Each generator required magnetic field windings using over 10 tons of copper wire wound with tolerances measured in thousandths of an inch to ensure perfect electromagnetic balance during high-speed rotation. The powerhouse construction revealed the economic advantages that AC technology provided beyond simple transmission efficiency. Where Edison's DC system would have required multiple generating stations distributed along the transmission route, Westinghouse's AC installation concentrated all power generation at Niagara Falls itself, taking maximum advantage of the waterfall's energy while minimizing construction and operational costs. The centralized approach enabled economies of scale impossible with distributed DC generation, larger, more efficient generators, centralized maintenance facilities, and specialized operating crews who could optimize performance across the entire electrical system. Tesla personally supervised the installation of his polyphase equipment during the summer of 1894, ensuring that generator alignment, voltage regulation, and phase synchronization met his exacting specifications. The Serbian inventor's perfectionist approach to electrical engineering had created a system where every component worked in precise harmony with every other element, from the water turbines that drove the generators to the transformers that prepared power for long-distance transmission. This systematic integration reflected Tesla's unique ability to visualize complete electrical circuits as unified systems rather than collections of separate components. The first Niagara generator began operation on August 26, 1895, producing electricity that powered local aluminum manufacturing facilities while engineers completed the transmission lines that would carry power to Buffalo. The aluminum plants provided an ideal proving ground for Tesla's polyphase motors, which operated industrial equipment requiring thousands of horsepower with efficiency levels that impressed even skeptical observers. These local installations demonstrated AC's reliability under demanding industrial conditions while generating revenue that helped finance the transmission line construction. Buffalo's electrical transformation began on November 16, 1896, when Westinghouse engineers synchronized the Niagara transmission system and illuminated the city's streetlights with electricity generated 26 miles away. The moment represented a technological watershed that definitively proved AC's superiority over DC for long-distance power transmission. Buffalo's residents witnessed electric lighting powered by Niagara Falls' energy, transmitted across distances that would have been impossible with Edison's DC technology, delivered through transmission lines that cost a fraction of what equivalent DC installation would have required. The success of Niagara transmission marked Edison's final surrender in the current war that had dominated American electrical development for nearly a decade. Edison Machine Works, recognizing the futility of continued DC advocacy, began manufacturing AC equipment in 1890, effectively abandoning the technology that had made Edison famous. The 1892 merger that created General Electric represented Edison's acknowledgement that his DC empire couldn't compete with AC's technical advantages, forcing him to retreat from the electrical industry that had been the foundation of his reputation and fortune. Edison himself had been marginalized within his own company during the transition to AC manufacturing, his opposition to alternating current technology creating friction with investors and engineers who recognized AC's commercial inevitability. By 1896, Edison had largely withdrawn from electrical manufacturing to pursue iron ore extraction projects in New Jersey, leaving the industry he had pioneered to competitors who embraced the technology he had fought so desperately to discredit. His departure marked the end of an era when individual inventors could control entire industries through patent accumulation and personal reputation. The broader implications of Westinghouse's victory extended far beyond electrical engineering into the fundamental question of how America would adopt new technologies. Edison's campaign against AC had relied on fear, political manipulation, and appeals to established authority rather than objective technical evaluation. His defeat demonstrated that superior engineering would ultimately prevail over marketing strategies, even when those strategies were backed by America's most famous inventor and enormous financial resources. The precedent established principles that would guide American technological development throughout the 20th century. Tesla's royalty payments from AC motor patents made him wealthy beyond his immigrant origins. But more importantly, his partnership with Westinghouse had created the technological foundation for America's electrical grid, the polyphase system that powered Buffalo from Niagara Falls would eventually span the continent, carrying electricity from generating stations to cities hundreds of miles away through transmission networks that Edison's DC technology could never have supported. Rural electrification, industrial automation, and the electrical conveniences that define modern American life became possible only because Tesla's engineering vision had triumphed over Edison's commercial resistance. The War of Currents concluded not with dramatic confrontation, but with the quiet acknowledgement that mathematics had rendered the conflict meaningless. Every major electrical installation ordered after 1896 used AC technology, making DC systems obsolete except for specialized applications like urban streetcar networks and telephone systems. American engineering had proven that technical excellence, supported by systematic analysis and rigorous testing, could overcome even the most sophisticated propaganda campaigns when the stakes were high enough to demand objective evaluation.